Hey again, it's Mr. Lum, and we're going to be doing our Unit 3 review on the January 2003 provincial exam. So let's get started with question number 15, and it says right here that we have solid barium hydroxide is added to water to prepare a saturated solution. Which of the following is true for this particular equilibrium? So let's write a quick little equation right here. So we have barium hydroxide is added to water. So we have BaOH2 is added to water, and it dissolves in the water and forms an equilibrium and makes barium ion and hydroxide ion. Okay, so there's two hydroxides here, and so therefore it makes two hydroxide ions. We start with solid, and we end up with aqueous, and it forms an equilibrium. Okay, and that's our equilibrium equation right here. So which one of these things is true? So the first one says an anion concentration equals cation concentration. That is very, very wrong. Say if this is well, this is very low solubility, but let's just say this is 0.1 molar, then this is going to be 0.1 molar, this is going to be 0.2 molar, twice as much. So this one is very wrong. The next one says trial Ksp is less than Ksp. If the trial Ksp is less than Ksp, then that means it is not at equilibrium. That means that it is it still wants to dissolve. Okay, so not at equilibrium. Blue litmus paper would turn red. That's only true if it's an acid. This OH minus is a base, so blue litmus paper would stay blue. Red litmus paper would turn blue. This one's also wrong. And D, the rate of dissolving equals the rate of crystallization. Or in other words, the rate of dissolving forward rate of reaction equals reverse rate of reaction. That is our answer right there. Okay, so 15 is D. Let's move on to question number 16. Now, it says right here, a saturated solution of lead iodide was subjected to a stress, and the following graph was obtained. Okay, so it says which stress was applied at time t1, right there. And what we see is that the concentration of these things have both increased. So what happened? So let's write a formula right here, a real quick one. PbI2. Now this is solid. Makes Pb2 plus and I minus, and there we have two of those. Now, this is a solid, so if we made a Ksp formula, it would just be something like this. Ksp equals the concentration of Pb times the concentration of I squared. Okay, that'd be our Ksp formula. Now, before we had this, now both of our products have increased. Both of our products have increased. So what has happened here is that since our products have both increased, Ksp is not equal. Ksp here is not equal to the Ksp over here, because all the products have increased. So what is the only thing that can change Ksp is a temperature change. What happened here? Well, the temperature increased. So the temperature increased, and it made more dissolve into, it made the reaction go forward and increase both of these concentrations. Okay? So this is our answer, temperature increased. Now a lot of people are going to be writing something like the addition of PbI2. A lot of people think, well, this PbI2 concentration increased and made it shift right. That's very, very wrong, because PbI2 is a solid. You cannot increase the concentration of PbI2. An increase in volume. If you increase the volume or added more water, what would happen is that these concentrations would decrease. Okay, the concentrations would decrease and it would force more to dissolve. The evaporation of water, well, what would happen is, since it's a saturated solution and we evaporate it would force the reaction to shift to the left. More solid would precipitate out. Okay, so this one's also not true. So again, only thing that it could be is temperature change. Temperature is the only thing that can change Ksp as well. Question number 17. And it says, which of the following would be true when equal volumes of 0.2 molar NaBr and 0.2 molar AgNO3 are combined? So we have NaBr and AgNO3. So let's take a look at our data table. So what we know about Na right here, Na is soluble with everything. Okay. Also NO3 is soluble with everything. Now let's take a look at Ag and Br. Now we see here Ag, or silver, or Ag, and Br, bromide, have low solubility. So that's going to form a precipitate. But NaNO3 is soluble, it will not form a precipitate. So let's go back to our question. So we have here NaBr, that's going to be aqueous, plus AgNO3, which is also going to be aqueous, and that's going to make AgBr, and I'm going to write this one in blue. This is solid, and I ran out of room here, but this is going to be NaNO3 aqueous. Okay, so our solid is going to be, or in other words, our precipitate is going to be AgBr. Okay, so no precipitate forms, that one's wrong. Precipitate forms of AgBr, that's correct. This one is wrong, this is very soluble. Precipitates of both of these, no, we know that this one is very soluble, so this one's also incorrect. So our final answer is 17B. Okay, let's go down to question number 18. And what we see here, it says, using the solubility table, so we got to go back to our solubility table, determine which of the following ions could not be used to separate sulfide from sulfate by precipitation. So which one cannot be used? Okay, so please make sure you read this slightly bolded word. So which one cannot be used? So in other words, which one is going to be either soluble with both, or which one is going to be insoluble or low soluble with both? Okay, so let's take a look. So scroll down to sulfate and sulfide. So which ones cannot be used? I'm going to go back here to see what our options are. Beryllium, calcium, barium, and strontium. Beryllium, barium, calcium, and strontium. Those are my 4 options that I have. So let's start with beryllium right here. Beryllium is low solubility, and low solubility here. It's under all others. Okay, so beryllium is not there. Barium. Barium is low solubility here, and barium is soluble here. Okay, so this one could be used to separate them. Beryllium could not be used. Okay, so this one looks like it's pretty good. Calcium has low solubility here, and calcium is soluble right here. So calcium could be used. Okay. And strontium. Strontium is low solubility right here, and strontium is so low solubility, and right here it has high solubility, or it's soluble. Okay, so this one could be used. So which ones, the question was kind of weirdly worded, which one could not be used to separate these two? Beryllium looks like it is the one that could not be used because it is soluble with both of these. So let's go back to our question now that we know it's beryllium. So again, beryllium is our answer right here. It is soluble with both. Okay, and these ones only soluble with one, insoluble or low soluble with the other. Let's do question number 19. Which of the following is true when solid sodium sulfide is added to a saturated solution of copper sulfide and equilibrium is re-established? Okay, so let's draw copper sulfide. So we have CuS, we have an equilibrium with CuS, and it is Cu2 plus and S2 minus. Okay, so we have an equilibrium here, solid, aqueous, aqueous. And what we did is we take some sodium sulfide and we add it to this equilibrium. Now sodium right here is a spectator ion, and so what we're doing is we're increasing the sulfide ion right here. So we're increasing this concentration right here. Okay, and what that's going to do is if we increase the sulfide ion, it's going to make the equilibrium shift left. We're going to have more CuS precipitate out, and therefore Cu2 plus is going to decrease. So let's go through some of these things right here. So we add sulfide ion, that's going to increase. Yeah, that's true. Cu2 plus, no, we just said that's going to decrease. So this is actually the opposite. S2 minus does not change. No, we said it's going to increase. And Cu2 plus does not change. No, it's going to decrease. So it's going to shift left, and this is going to decrease right here. Okay, and more is going to precipitate out. Okay, so our answer right here is 19A. Okay, moving on, let's do question number 20. And it says, which of the following describes the relationship between the solubility product constant, Ksp, and the solubility S of PbI2? Okay, so first I'm going to write PbI2, and that is going to form an equilibrium, Pb2 plus aqueous, and 2I minus. So it gives us the solubility of PbI2. So it's saying if PbI2 right here, or lead iodide, has solubility at equilibrium, and we can give it a value. So maybe it's like 0.1 molar. But what we're going to do, instead of calling it 0.1 molar, we're just going to give it a variable, or just a value, and we're going to call it just S. So this is S. So what's the concentration of Pb2 plus? Well, this is also going to be S. Okay? Because it's a 1-to-1 ratio right here between these two things. Now this one is a 1-to-2 ratio right here, so this is actually going to be twice the concentration of this one. So this is going to be 2S. Okay, and that is the relationship between the concentration of PbI2 to the concentrations of Pb and 2I, right? S2S relationship. But the question is asking, what is the relationship between S and Ksp? So let's write a Ksp formula. Ksp equals the concentration of our products, Pb2 plus, over the concentration of our reactants. Now our reactant is a solid, so we don't have a concentration of that. And we put that in here. And since there's a 2 right here, we put squared. Okay? So let's put in the concentrations right here and put in some values where these numbers are, these symbols are. So again, Ksp equals, now Pb is represented by S, and I's value is 2S. And we have to square that. Okay? So again, we just do a little bit of math right here, and we go S. Now 2S times 2S is 4S squared, and S times 4S squared, well, our Ksp equals 4S cubed. And I'm already, and hopefully you are already seeing, that that looks like this one right here. Okay, so our answer is 20B. Okay, moving on. Okay, and let's move on to question number 21. And this question says, which of the following saturated solutions will have the lowest concentration of sulfide ions? And we're given barium sulfide, calcium sulfide, copper sulfide, and zinc sulfide. So we're going to need to use our data table to help us answer these questions. So barium, calcium, copper, and zinc. So let's take a look at our data table. And we have, on our data table, we know it's barium, calcium. So let's write it down. Barium sulfide, calcium sulfide, copper sulfide, and zinc sulfide. So we see here, now, barium is soluble, and same with calcium is soluble. So these are going to have very, very high solubilities. Now, copper and zinc are both low solubility, so how do we figure out which one is it? We know it's going to be one of these two answers, copper or zinc. Now we have to figure out which one has the lowest concentration of sulfide. We know it's going to be one of these two. We just don't know which one from this table. So we're going to go down and we're going to look at this table down here. So again, we know it's either copper or zinc. So we can see copper. Let's go back up a little bit. Copper sulfide right here is very, very, very low. It has a Ksp of 6.0 times 10 to the minus 37. So that means very, very, very little sulfide ions are going to be present. Now let's take a look at what zinc's is. Now zinc is also very low, times 10 to the minus 25. However, it's not quite as low as the copper one. So copper has a much, much smaller Ksp value. And if it has such a small Ksp value, and we know that Ksp equals products over reactants, or in other words, Ksp, one of the products is sulfur or sulfide. And since this number is much, much bigger than copper's, this concentration is going to be much higher. So the lowest concentration is going to be that one with copper sulfide right here, minus 37, 10 to the minus 37. Okay, so we can go back to our test right here and say 21 is here. Okay, what would have the second lowest sulfide concentration is this one, zinc. Now these two up here are soluble, so they would have quite high sulfide concentrations relative to these two. Okay, let's do question number 22. What is the solubility of strontium fluoride? And this is our last multiple choice question for Unit 3. And for this one, we need to get a number from our data table. So strontium fluoride, here it is right here. And we see it's 4.3 times 10 to the minus 9. So I'm going to memorize that number. And 4.3 times 10 to the minus 9. And we're going to write it here to do some few calculations on it. So Ksp equals 4.3 times 10 to the minus 9. Okay, and it says, what is the solubility of this one right here? Now, a lot of people are going to be just looking right here and seeing C, 4.3 times 10 to the minus 9. No, this is Ksp. Ksp and solubility are not the same. Remember, Ksp is the solubility product. Solubility is measured in molarity. Ksp doesn't have any units. So what we want to find is this maximum concentration of strontium fluoride. And let's do show it right here. So we have SrF2, and that forms an equilibrium reaction. Now there's F right here, so F minus. Now there's two of these, so we need to write a 2 right here. Now if I were to make a ratio of this, this would be 1, or I'm just going to give this a value like x. And so this is a 1-to-1 ratio, so this would be x2, or also. And this is twice that of strontium, so this would be 2x. Okay. Now, if I were to make a Ksp formula, Ksp would equal this times this. Now this is a 2 in front of it, so it would be squared, and therefore strontium, or in others we could just write it like this, I guess. And then let's replace these values in here. So again, Ksp equals x times 2x, forgot a little thing right there, very important, squared. Now let's replace all of our numbers. And again, 4.3 times 10 to the minus 9 equals 2x times 2x is 4x squared, times another x is 4x cubed. Okay, so now I'm going to solve for x. Again, we're going to just do a little basic mathematics here, so I'm just going to move my equation over here where there's a little bit more room, and I'm going to go 4.3 times 10 to the minus 9. I'm going to divide both sides by 4. So if you want to see, what I'm doing is I'm just going divide by 4 on this side and divide by 4 on this side, and that is making this go away. And then I'm going to do this to both sides. 1/3 to the power of 1/3. And so in other words, it's going to be 1/3. and that is going to equal X. Okay, and X happens to be the solubility of SrF2, or strontium fluoride. So we plug this into our calculator, 4.3 times 10 to the minus 9 divided by 4, and then we go to the power of 1/3, and I come up out of my calculator, I get a number that looks like this. X equals 1.02 times 10 to the minus 3. Now this is 2 sig figs, of course, so I need to change this to 2 sig figs, so it would be 1.0 times 10 to the minus 3. And that is our answer right here, and that happens to be one of our multiple choice answers right here, and it is D. Okay, so it takes a little bit of math. I guess that's why this particular one is worth 2 marks. But our answer is 22D. Good. Now we're going to move on to the written section of this. I'm doing the Unit 3 of the written section.